Greetings, Panthers. Part 2 of a two-part video explaining Dalton's law of partial pressures. And this one we're going to take a look at collecting gas over water. This is a great way to collect a gas sample from a chemical reaction. If you recall, in the last video we mentioned this is the displacement reaction between zinc and hydrochloric acid. So zinc solid plus 2HCl aqueous yields zinc chloride aqueous plus H2 gas. And also recall in the last video we mentioned that as these hydrogen gas bubbles percolate their way up through the water, they're actually picking up water vapor due to the vapor pressure of water. So we actually have a mixture of gases in here. We have mostly hydrogen and a little bit of water vapor will be in there due to the vapor pressure of the water. So here's an example question. Suppose you collect 0.5 liters of hydrogen over water, which is 26 degrees C, and the total pressure of the collected gas is 745 millimeters of mercury. Pretend there's a little pressure gauge on here and you're able to measure the total pressure of the gas. Vapor pressure of water at 26 degrees C is 23.8 millimeters of mercury. Two questions. How many moles of gas are in the flask? In other words, what's the total number of moles that get collected here? And how many moles of this gas are hydrogen? So this might be a good place for you to stop the video and see if you can work on this problem yourself, and we will come back and solve each of these problems in turn. So the first problem we want is how many moles of gas are in the flask? In other words, N total is what we're trying to find. So we're going to use P total V equals N total RT. And if we look at this equation, we look at the variables we have. Volume we know the volume. We know R always. We know the temperature, and we're given the total pressure. So this actually is a fairly straightforward problem. It's just like an ideal gas PV equals nRT problem. Remember, R has specific units. R is equal to 0.0821 liter atmospheres per Kelvin mole. So we need to get our temperature into kelvins, we need to get the volume into liters, and pressure needs to be in atmospheres, okay? So liters, atmospheres, kelvins, and moles, those are our units. I'm gonna rearrange this equation and solve for N total because that's really what we're actually interested in. So N total is equal to P total V divided by RT. And I'm just going to write down what those different parameters are. So P total is going to equal to 745 millimeters of mercury times 1 atmosphere for every 760 millimeters of mercury. Millimeters of mercury cancels millimeters of mercury, and that is going to equal to 0.980 atmospheres. V is equal to 500 milliliters, we're actually given it in liters, 0.500 liters. Temperature is equal to 26 degrees C plus 273.2 Kelvin. So that is going to equal to 299.2 Kelvin. Okay, then we just need to plug into our PV equals nRT equation. So N total is equal to 0.980 atmospheres times 0.500 liters divided by 0.0821 liter atmosphere per Kelvin mole times 299.2 Kelvin. Kelvin cancels Kelvin, atmosphere cancels atmosphere, liter cancels liters, and that leaves me 1 over moles. So N total is going to equal to 0.0199 moles. All right, that answers this question. And remember, that's really hydrogen plus water. So that's really the number of moles of hydrogen plus the number of moles of water. Okay, the second question is, how many moles of this gas are hydrogen? There's actually two different ways you can solve this problem. I'm going to encourage you to stop the video now, see if you can solve it, and I'm going to show you both different ways that you can solve this problem. So Let's recall our fundamental. This is Dalton's law of partial pressures. P total is equal to pH2 plus pH2O. We are trying to find the number of moles of hydrogen. So that's the one we're going to need to isolate. So pH2 is going to equal to P total minus pH2O, or in other words, this is going to be equal to 745 millimeters of mercury, that's the total pressure, minus 24 millimeters of mercury. Now I know it says 23.8, but for significant figure reasons, we'll just keep the significant figures consistent with the total pressure. So this is going to equal to 721 millimeters of mercury. That's the pressure due to hydrogen. So method 1 would look as follows. pH2 is equal to the mole fraction of H2 divided by P total. pH2 divided by P total is equal to the number of moles of hydrogen divided by the total number of moles. Now we found the total number of moles above. So we have the partial pressure due to hydrogen, we just found that. We're given the total pressure in the original equation, and we have the total number of moles from the prior problem, so that will enable me to find the number of moles of hydrogen. By the way, this is method number 1. There's 2 different ways to do it. You may not have done it this way, and we'll show you how to do the other way. So pH2 divided by P total times N total is going to equal to the number of moles of hydrogen. In other words, this is going to be 721 millimeters of mercury divided by 745 millimeters of mercury times 0.0199 moles. And that comes out to 0.0193 moles hydrogen. Okay? That's the first method we can have for finding out the number of moles of hydrogen given this problem. But some of you may not have done it this way, and that's okay, because there's actually a second way that you can do it. And actually this might be the one that was more popular to do. So we could do this. P hydrogen times V equals N hydrogen RT. So P hydrogen times V over RT is equal to N hydrogen. We're looking for the moles of hydrogen gas. We can use that PV equals nRT specific for hydrogen. We know the partial pressure due to hydrogen. We found that before. And we can just do an ideal gas equation. This would be the second way we could do this. Either one is equally valid. We're going to end up with the same answer, as you can see. We've only got one problem we need to be aware of. Remember the units on R, liter atmosphere per Kelvin mole. We have volume in liters. We've already found the Kelvin temperature, but this pressure is in millimeters of mercury. So we're going to need to convert that into atmospheres before we're allowed to do this calculation. So let's do that first. The pressure of hydrogen is equal to 721 millimeters of mercury times 1 atmosphere for every 760 millimeters of mercury. Millimeters of mercury cancels millimeters of mercury. And this is going to equal to 0.949 atmospheres. All right, so now we're going to plug into our PV equals nRT. 0.949 atmospheres times 0.500 liters divided by 0.0821 liter atmosphere per Kelvin mole times 299.2 Kelvin. And I'll use my Christmas colors. Atmosphere cancels atmosphere, liter cancels liter, Kelvin cancels Kelvin, and we're going to be left with moles. And when we do all that, the number of moles of hydrogen also equals 0.0193 moles hydrogen. Either way is an acceptable answer. One is not preferred over the other. Either way is a valid way of doing it. Some situations you'll have more information than others, so you may not always be able to do this. This is always a decent equation, but let's just recap what we did here. We have one way of calculating based on the partial pressure of hydrogen. We have a second way of calculating based on the partial pressure of hydrogen. Either one is valid, and just depending on the problem, you may have one preferred over another. One might be a little bit easier than the other, but we end up with the same answer in either case. Okay, thanks for watching.